I didn't know this actually.
Okay, let me just talk a little bit about what else we have to cover. So I want to talk about graphing log functions, just to be able to, because we know that logs and exponentials are very much intertwined with each other. We can convert from one form to the other using, because we know they're inverses, so they have a way of canceling or undoing each other. And I want to be able to graph from that perspective to begin with. So to graph an exponential and see that that relationship from a graphical perspective as well between exponential and log functions. But it's not the most efficient way to graph. But I'm going to start off with it so we can kind of see that, okay, I can, if I have an exponential, I can get to my log function just by doing this one thing. And then there's only a couple problems here, and then I would like to be able to start with the graphing log function the way that we're going to do it, which is a lot more efficient. But we can just use log properties to get to where we need to go. And that way we can kind of cover a lot of 10.09 today. And then we can spend Monday and Tuesday doing test review, because I know that there's some students who may want to take the test early on Wednesday instead of Thursday. So you guys have that option if you want to. But if not, then you can use Wednesday as a review day. I can give you an extra review sheet to practice. I made 3 additional test review worksheets. I'm going to upload them onto the website, provide the key. But I can have help sessions both Wednesday lunch and Thursday lunch, or 4th period. If you, yeah, but there's probably more review sheets than you have to do. So, but I'm going to provide those review worksheets in case you want that extra practice. So it's really up to you. But really, the only thing required is just the review worksheet in your packet. Okay, any questions right now? Okay, so let's go to page 22. And I want to talk about log functions from the perspective of exponentials. So let's talk about exponentials, because exponentials, I think, something that we are more familiar with. And let's start with what's more familiar, and then we can move on to how logs fit in. So 2 to the x, let's go ahead and find order pairs that are easy around 0. So I'm going to pick order pairs around 0. Let's see. So let's choose -1, 0, and 1. Okay, so the function is y equals 2 to the x. This is an exponential function because you have a base that's a constant and you have a variable, an exponent that's a variable. Okay, so that's an exponential function. All right, I'll see you Monday. So let's start by inserting these values one by one into the exponent variable here. So 2 to the -1. Okay, what's 2 to the -1 equal to? So let's test it out. 2 to the -1 is same thing as 1 over 2. Yeah, so 1/2. Okay, so okay. 2 to the 0. What's anything to the 0 power? 1. And 2 to the first power is 2. Okay, so I think just by 3 points, we should be able to get a good feel for what the graph will look like. So let's plot those points. So your exponential function is going to hover right above the x-axis, and it's going to suddenly rise really quickly. So it's actually getting infinitely close towards the x-axis. It just never reaches it. And so we call that the horizontal asymptote. So let's gather some information about this exponential function here. So domain, what do you think the domain is for this exponential function? Yeah, possibility, right? It just stretches in both directions with no breaks. Okay. What do you think the range is for this function? Okay. Right, so we want to look at y values. I'll look at the lowest to the highest y value. Lowest y value is 0, highest y value is infinity. Asymptote is a horizontal asymptote, so y equals 0. Yeah, we're going to see a distinction between y and x. So if we see a horizontal asymptote, we always want to make sure to give it the full name. We just say y equals 0. X-intercept, does the graph ever touch the x-axis? No. Okay, so there's none. Okay, now the inverse of y equals 2 to the x. Let's see if we can discover what the inverse is. So the way we find inverse is we swap the x and y value of the exponential function, and we're going to solve for the new y. So I'm going to go ahead and start that process. So here's my exponential function. I'm going to swap the x and y. So I get x equals 2 to the y. Okay, but now I want to solve for y. But if I want to solve for y and y is stuck in the exponent, what can we do to both sides to get that exponent to come down? What do we recently learn to allow for that exponent to move? Take the log of both sides, okay? But we're going to take the log of both sides. That's strategic. We want to pick the base that will match, which will allow things to clean up nicely. So I'm going to take the log base 2 of both sides. And you're going to see there's something nice about taking the log base 2, because if I have log base 2 of 2 to the y, right, 2's cancel out, the log goes away, and the y drops down. So y is equal to log base 2 of x. So this is the inverse of y equals 2 to the x. Okay. This is not the way that I want us to graph down the road, but I want us to see that connection here. The relationship here between inverse functions is that their x's and y's will be flip-flop with each other. So instead of negative 1.5, what do you think the order pair is going to be on my log base 2 of x function? Yeah, 0.5, negative 1. Okay. I know my order pair is 0, 1, so on the inverse, it must be what? 1, 0. I know my order pair on my exponential is 1, 2, so on my log function, it must be 2, 1. Let's plot these points and see what the graph will look like. Okay, so 0.5, negative 1, 1, 0, and 2, 1. Okay, let's follow the path of this graph based off of those order pairs. Okay, now look at these two graphs here. You have the exponential, you have the inverse, in this case, a log base 2 of x. And anytime you have a function and its inverse, there's always going to be this visual, this kind of visual feel to it, where if you can imagine folding across the line y equals x, that's the equation of this diagonal line here. Can you imagine these two graphs kind of overlapping each other? Okay, so that's the perspective. Anytime you have a function and its inverse, you can always fold the graph over the dotted, this y equals x dotted line, and the graphs will always overlap each other. And the reason why is because every ordered pair that lives on one function, the flipped version is going to live on the other graph. So if there's 1, 0 that lives here, then 0, 1 will live on the other graph. If there's 1, 2 that lives here, then 2, 1 is going to live on the other graph. Okay, so here is the log function. So all your log functions will kind of have this shape. Okay, it'll rise really, really quickly with a vertical asymptote, and then it's going to kind of gently there will be a more gradual slope as it moves away from that asymptote. Okay, what's the domain for this log base 2 function? So we start furthest left. So we're looking at x values. The smallest x value we see is going to be this asymptote, this x equals 0. And then the furthest right the graph is going to go is going to be positive infinity. So our domain is from 0 to infinity. Range, what's the range for my log base 2 function? Yeah, right. You look at your y values, it stretches with no bounds, goes all the way down, and goes all the way up. Asymptote? X equals 0, right? Not a horizontal asymptote anymore, it's a vertical asymptote. And what's the x-intercept? On 0. X-intercept is where the y is 0. Okay, there's another observation that I want you to make. What do you notice about the domain and range of my 2 inverse functions, or the functions that are inverses of each other? They're flipped, right? That kind of makes sense, right? If all the ordered pairs are flipped, then it should make sense that the domain for one is the range of the other, and range of one is the domain of the other. Right? Everything is kind of, flipped between a function and its inverse. They both have asymptotes, but one is horizontal and the other is vertical. X-intercept, right? 0, 1 is not an x-intercept here. So here, okay, another relationship here is this one does not have an x-intercept, but it does have a y-intercept. Meanwhile, this does not have a y-intercept, but it does have an x-intercept. So we kind of see that. So I want you to see that intertwined relationship algebraically as well as graphically. Okay, so that's the big key that I want us to take away here. So what do you notice about two graphs? Order pairs are switched between function and inverse. Y equals 2 to the x. Okay, so really, we're not going to be graphing any exponential functions on the test. So I just want us to see that relationship. But then now that we see that relationship, I want to kind of transition over to just being able to graph a log function as efficiently as possible. Okay. And we're doing it without a calculator. So I want us to kind of talk about properties that will lead us to that. So I want us to skip the bottom of the page 10.08, because I don't want us to keep going back to the exponential and get to logs. I want us to be